Okay, good afternoon, class. Before I go with the material I prepared for today, are there any questions with regard to the subject matter? Any questions? So anything that was you're supposed to have studied last week, may mga tanong ba? Yeah, can you hear me okay? Can you give me a thumbs up if you can hear me okay? I just want to make sure that I'm coming across well. Okay, good. No? Sige, I prepared some material, but I also want to go through some of the material which we were supposed to cover last week. No, just go through it very shortly. No? Okay, so just maybe some sort of review also, no? So with respect to conduction mechanisms, in semiconductors. So we talked about drift last time. So number one, we talked about drift. And this is the tendency of carriers to move in the direction, or to move in the presence of an electric field. So let's say I have a semiconductor material here. Okay. And then this is electrons. No? And this is also holes, electrons and holes. Okay. Let's say this is my electron and this is my hole. If I have an electric field, let's say in this direction, okay, where will my electron go? Will my electron go right or left? Can I hear a shout out? Sigaw lang yung tanong. Will my electron go right or left?
Left.
Okay, left, no? So this electron will tend to go to the left. Then on the other hand, the hole will tend to go to the right. Okay. Now, since the electron is moving to the left and current is defined as the movement of positive charges, you have electron current moving this way, no? Let me call this IN, no? Electron current. And then holes are moving to the right, so your positive charges are moving to the right. So you also have a hole current moving this way, no? And therefore your total current will be your current due to your electrons plus your current due to your holes. And we defined what we called current density. No, this is a current per unit area. Okay. So if the cross-sectional area of this is A, for example, no, kung yung area nito is A, J is equal to I over A. And then we showed that, okay, for drift, so we're talking about drift, J, P, drift, this is your drift current density due to holes is equal to Q, P, use of P times your electric field. Okay, times the magnitude of your electric field. Okay. So Q, this is your electron charge. So we know this to be 1.6 times 10 to the minus 19 coulombs. Okay, P is your, okay, ano ibig sabihin ng P? P is your hole concentration So this is number of holes per cubic centimeter. Usually we specify it in terms of cubic centimeter. Use of P, this is called the mobility of holes. Okay. This is a measure of how mobile the hole is in the solid. And this is a dimension of sorry, nawala yung okay. Your mobility of holes, this is a dimension of centimeters per volt second. Oh, this is in centimeters per volt second. Then of course your E is your electric field intensity. This is volts per centimeter. So that's for drift, no? And for your drift current due to electrons, this is Q N, use of N times the magnitude of E. Where itong use of N ngayon, this is your mobility of electrons. So yung J total natin, J total due to drift, will just be the sum of these two. Will be the sum of this plus the sum of this. So this is going to be Q. Okay, because Q is common for both. No? And then you have P, use of P, plus N, use of N, multiplied by the magnitude of your electric field intensity. And this is now what we call our conductivity. We give this the symbol sigma, that is your conductivity. Where sigma is equal to 1 over rho, rho is your resistivity. No? Ito yung tinatawag nating resistivity. Okay? So that's drift. No? Things to take note of, the mobility of electrons is much higher, significantly higher than the mobility of holes. No? Yung electron has mas maliksi yung electron, no, so to speak, no. Mas nakakagalaw siya kaysa sa hole. It's easier for electrons to move rather than holes. As a matter of fact, the mobility of your electron is anywhere from 2.5 to 3 times the mobility of your hole. So if you have an N-type semiconductor, expose it to an electric field, expect the electrons to move faster than if you had a P-type semiconductor exposed to the same electric field. No, expect the holes to move slower than the electrons. Later on, you're going to see that will have an effect on the performance of your semiconductor device, whether the carriers are due to electrons or the carriers are due to holes. Okay, so that's for drift. Then the other thing that I want to review with you is diffusion. Diffusion. So this is the tendency for the concentration of the carrier to become equal over a certain volume. And the analogy I gave last time was when you drop ink into a container of water. If you drop ink into a container of water, the ink is going to disperse. And the reason why the ink disperses is because of diffusion. there's a tendency for the ink concentration to become constant over the entire volume of water. So it's the same thing with carriers. Okay. So let's take into consideration, for example, you have a solid. No? So let's say this is a solid. And you manage to inject impurities. You manage to inject impurities into one end of the solid. So kunwari holes, no? Or acceptor impurities. We're injecting acceptor impurities, so effectively we're injecting holes. So after a while, what's going to happen to the concentration of the impurities in the solid, no? Okay, because of diffusion, ganito yung mangyayari, no? Here you have a high concentration of holes, no? High concentration of holes. Sorry. Okay, here you will have high P, and here you'll have a low value of P, no? Where P is your concentration of holes. That is because, okay, the impurities will diffuse. The holes will diffuse toward the right. And eventually you're going to get a concentration gradient. There's going to be a gradient, a concentration gradient. Okay. So let's, I'm not going to explain the physics behind it anymore, no? But your concentration gradient is going to end up like this, no? If you take a look at P versus X, it's going to be exponential. Okay. So there are going to be holes diffusing in this direction. Okay. Your JP, due to diffusion, okay, is going to be proportional to negative dP by dx. It's going to be proportional to negative dP by dx. Now, why negative? No? Because take note that here, P is decreasing, and therefore dP dx is negative. Okay. On the other hand, your current is from left to right. So this is your current, I's of P. It is from left to right. And then this is a negative slope. So this current is going to be proportional to the negative of the negative slope. That's why it's going to be proportional to negative dP dx. As a matter of fact, JP, due to diffusion, okay, is going to be minus Q d of P dP by dx, where dP, this is called your diffusion constant. If you had a non-uniform distribution of electrons, okay, so for non-uniform distribution of electrons, you have a Jn due to diffusion, and this is now going to be N, this of N, dN by dx. Sorry, Q, not N. No. Q, this of N, dN by dx. Okay, bakit walang negative dito? Okay. because the direction of flow of electrons is going to be opposite the direction of where your electron concentration is decreasing. It's going to be opposite. Kasi kung ito yung N versus X, sorry. The direction of flow of electrons will be this way, but your current will be this way. The direction of flow of current will be opposite the direction of flow of electrons, which is proportional to the negative of d and dx. That's why nawawala yung negative sign. So J due to diffusion will just be Jp due to diffusion plus Jn due to diffusion. Okay, let's take the case of a non-uniformly doped semiconductor. Okay, iba to dito sa injection, ano? Here we're injecting impurities into one of the surfaces. There are several ways of doing that. We'll take that up later on, but this is a case of injection. Here, the semiconductor material to start with is non-uniformly doped. So we're talking about, for example, if this is your solid, no? So if you take a look at the doping, so this is the doping profile. The doping profile. So here it is heavily doped. And here it is lightly doped. Okay, let's consider a linear doping profile. So let's consider a linear doping profile. So kunwari N, donor impurities. Okay. So this is going to be N. ND, no? This is going to be your donor impurity concentration, ND. So let's say it varies linearly this way. No? So dito sa left side, your donor impurity concentration is high. As you go to the right, your donor impurity concentration goes low. And later on, when I discuss the p-n junction, you're going to see why this might happen. Okay, what's going to happen? The instant this solid is created, there's going to be now a non-uniform concentration of electrons, of free electrons. That is assuming total ionization. So I explained total ionization last time. No, total ionization is when all of the impurities are ionized. That is, all holes of an acceptor impurity accept an electron, and all free electrons in a donor impurity are promoted to the conduction band. So that's total ionization. So if we assume total ionization, there are going to be more holes on the left side than on the right side. No? And therefore, there's going to be a migration of more electrons on the left side than on the right side. No? So what's going to happen here is there's going to be a migration of electrons this way. Migration of electrons. No? So what will happen if the electrons migrate? After a while, the left side is going to be positively charged, and the right side will eventually end up negatively charged. Imagine ninyo yung electrons, because there's a non-uniform doping concentration, the electrons will move from left to right. As the electrons are moving from left to right, the atoms that the electrons move behind become net positive. And as the electrons move left to right, the atoms on the right, or because of the extra electrons on the right side becomes net negative. So after a while, your solid is going to look like this. The left side is going to be positive with respect to the right side. And when you have a charge distribution this way, you learn this from electromagnetics, probably have taken this up in physics also. There's going to be an electric field that will develop in this direction. Kasi yung left side natin positive, yung right side natin negative, magkakaroon ka ng electric field that develops in this direction. Now, what happens when you have charge carriers in the presence of an electric field? We just took this up. Can somebody shout out an answer to me? What happens when charges are exposed to an electric field? Shall I call out people at random? Anyone? Any volunteer?
Drift, sir.
That's right, no? In the presence of an electric field, nagkakaroon ng drift. Okay. Now, if my electric field is left to right, okay, can you continue your answer, no? The person that answered, sorry, I didn't get your name. If the electric field is left to right, and these are electrons, what direction will the electrons flow?
Right to left, sir.
From right to left. That's right, no? So ano mangyayari, no? So because of this electric field, you're now going to have electrons. No? Electrons will drift left, no? Okay. So you have electrons diffusing right. On the other hand, you also have electrons drifting left. At some point, this will cancel each other out. Cancel each other out. So that your I total will be equal to 0. So imagine, because of diffusion, because you have a non-uniform donor concentration, you have electrons going this way. And then as your electrons are going this way, you're building up an electric field from the left to the right. And as that electric field builds up, you have electrons going the opposite direction of the electric field. So meron kang electrons diffusing, meron kang electrons drifting, they cancel each other out. So the net current is equal to 0. So this is at equilibrium. However, at equilibrium, there's going to be a potential difference. So at equilibrium, there's going to be a potential difference existing between the left side left and right. Whenever you have an electric field, that means there's a potential gradient, no? There's a potential difference. Okay. With respect to the electrons, For example, no? If this is your electric field, okay, with respect to positive charges, the left side is of a higher potential than the right side. This is with respect to positive charges. Why? No? If I get a positive charge and I hold it in place here, it is going to be harder for me to hold it in place here than for me to hold it in place here. In other words, it will have more potential energy here than here. No? That's for your positive charge. On the other hand, if I get a negative charge, I try to hold that charge in place here, it's going to be more difficult for me than to hold it here. No? So my potential for electrons is going to be higher on the right than on the left. No? So the potential energy or the potential, the potential for electrons, okay, is higher on the right side than the left side. Ang mangyayari nito, if you take now a look at your energy band diagram, so this is going to be my energy band diagram, and this time, this is with respect to X. No? If I take a look on the, so this is E, no? And this is the energy of electrons. The energy band diagram describes the energy of electrons. No? If I take a look, if this is my EC, no? And this is my EV, okay. Okay, let's say at this point, let's say this is the end of my solid, this would have risen this way. Okay, you call this band bending. As you go to the right, the potential energy of your electron is increasing. On the other hand, if you take a look at the Fermi level, so we took up the Fermi level. The Fermi level will be the same, no? So this is E of F. Okay, take note that for an N-type, we said the Fermi level is higher than the intrinsic Fermi level. No? Pag N-type, yung Fermi level natin goes up toward E of C. Pag P-type, yung Fermi level goes down toward E of B. Now, this is going to be flat, no? Because you can only have one value of E of F for the entire solid. For an electronic system, you can only have one value of E of F. This is the probability that the electrons occupying that particular level is equal to 1/2. That's the definition of your Fermi level, or if you recall your Fermi function. So if you don't remember the Fermi function, please review the material from 1. So this is how your energy band is going to look like. Your energy band diagram is going to look like along the X direction if you have a non-uniformly doped semiconductor. Are there any questions? Are there any questions? Because I'm now going to move to the material intended for this particular session, which is now p-n junctions. So before I move into p-n junctions, I'd like to ask, are there any questions? Whenever people have no questions, for me, it's only one of two possibilities. No, one is they understood everything, or second, they understood nothing. So I'm hoping it's not the latter. By the way, it's going to be very difficult for you to keep up with these supplementary lectures if you don't read the material beforehand. If this is the first time, that you're encountering these terms or these explanations, then mahihirapan kayo talaga. The way the course was designed was all of the material is given to you beforehand. We encourage you, to read the material first, and then ideally nga sana dapat pagdating dito sa synchronous sessions natin, nagtatanong na lang kayo ng questions, no? Although from experience, I realized that nobody ever asked questions. So what I usually do is I just reintroduce parts of the material which I feel might need better explanation. But like I said, if this is the first time that you're seeing this material, medyo mahirapan kayo. So try to go through the material before the supplementary lectures. Okay, so let's go to the next topic, and this is your p-n junction. Okay, the discussion of p-n junctions is going to be it's going to be rather qualitative. That's one of the things that happened to this course when nag-pandemic, from being highly theoretical, we made the discussions, we toned down the discussions, we made it more qualitative. Okay, first of all, how do you create a p-n junction? Okay. So typically, you start with, let's say, a p-type semiconductor. No, sorry. Typically, you start with an n-type semiconductor. Okay. And then through one end, you diffuse acceptor impurities from one end. So dito, magdi-diffuse tayo ng acceptor impurities. Okay, this is done in a semiconductor fabrication facility. What they do is they put the material, the semiconductor material, they put it in what is called a diffusion oven. Okay, that diffusion oven is void of any gases that could react with the semiconductor. No, so if there are gases inside the diffusion oven, it will be an inert gas, a gas that will not react with the semiconductor material. And then inside the diffusion oven, they are going to introduce now your acceptor impurities. And they do it in such a way that the acceptor impurities are introduced only at one end of the semiconductor. So the same principle of diffusion. If you have a non-uniform concentration, the tendency will be for the concentration to become uniform. So your acceptor impurities will now find its way inside the solid. So these are now your acceptor impurities. And after a while, you expect there will be now a distribution of acceptor impurities where the left side will have a higher concentration of acceptor impurities than the right side. So if you take a look at your diffused, let's say this is a graph, versus X. This is your diffused acceptor concentration. Okay. The nature of diffusion is almost always going to be exponential. It's going to be something like this. Okay. That's going to be your diffused acceptor concentration. So mas mataas yung acceptor concentration sa pinakakaliwa, and then leveling off as you go down. No? Now, if you take a look at, so originally this was N-type, sabi natin, no? This is N-type. So originally that had a donor concentration or something like this. Okay. So if we get the net concentration, the net net donor concentration, that's what I want to get, ano? The net donor concentration is going to look something like this. Here, where ND is equal to the diffuse acceptor concentration, is going to be 0. The net donor concentration is going to be 0. No? Okay. And as you go from this point onward, okay, nawawala na yung acceptor impurities, and eventually babalik sa ND yung concentration natin. No? So this is ND. Okay. This is now going to be negative NA, where NA is this. No? This is NA. Because if I subtract this plot from this line, more or less this is what I'm going to get. No? Itong baba, ito yung makukuha ko. No? Where the distance now between this and this is now going to be the distance from here to here. No? Okay, that's going to be my net donor concentration. Okay, so I show it again here. This is going to be my net donor concentration. Now what we actually want, so this is the actual profile of my net donor concentration. But this is what we actually want. This is the step junction idealization. So when we analyze, in analyzing a PN junction, we will assume a step junction. So ito yung i-assume natin, itong shape na to, no? Anyway, you're going to find out later on that by making this assumption, we will not suffer much in terms of precision, no? Okay. We will not suffer much in precision from making this assumption. Okay. So at the end of the day, what do we have? We have this. Okay. Where the left side we can consider to be a p-type with concentration with acceptor concentration Na. No? Sorry, no? Dapat tapat tong dalawang to. And then the right side is an N-type with donor concentration ends of D. N sub D. Okay, so this is now your PN junction. The interface from the P type to the N type, this is your PN junction. Okay, you cannot make a PN junction by gluing together a P type and an N type. You cannot do that because at the interface between the P and N, the crystal structure of your solid has to be consistent. Remember what I said, that between a P type and N type or an intrinsic semiconductor, it will look the same, it will feel the same, it will smell the same. You won't be able to tell the difference physically. So if you're inside this particular semiconductor material, as you go from the P type to the N type, you're not going to notice any difference. If you were Atoman and you go inside, you're not going to notice any difference. Okay, but that is because the crystalline structure is maintained from the P type to the N type. So hindi ka pwedeng gumawa ng PN junction na ipagdidikit mo lang yung P type at saka yung N type. No, you cannot do that. Okay, let's take a look at the energy band diagram. No? So this is your P type and this is your N type. Okay. So this is the band diagram at the instant the junction was created. So kunwari ano no, sige, kunwari na lang pinagdikit natin yung dalawa, that's how we did it, no? At that particular instant, this is what your energy band diagram would look like. Okay. This is the value of EC. Okay, that is the lowest possible energy an electron can have to be able to be promoted to the conduction band. This is the value of EV, the highest possible energy your hole can have, okay, or your electron in the hole can have, okay. And then you have your intrinsic Fermi level, E of I. And then remember that in a P-type, your Fermi level is below E of I, and in an N-type, your Fermi level is above E of I. Okay. Now, what is going to happen? So at the instant that the connection is made, because of diffusion, your holes will diffuse from P to N. And then your electrons will diffuse from N to P. So meron tayong holes pag ganito, meron tayong electrons pag ganito. What do you expect to happen when electrons and holes meet? Anyone? Anyone wants to guess? Ano mangyayari when electrons and holes meet? Any guesses? Yes, Ryan?
Sir, will the electrons drift towards where the holes are and occupy their space?
First of all, it's not drift, no? It's diffuse.
Oh, diffuse, sorry. Will it diffuse towards where the holes
it's
are?
diffuse. Yeah. The electrons will yeah, no? That's what's going to happen here, no? Your electrons here, because this has a high concentration of electrons, here you have a lower concentration of electrons. Electrons will go to the left, no? And your holes will go to the right, no? So my question is, what do you think will happen when an electron and a hole encounter each other? Okay, yes.
They will combine.
Yes, they will. The chances are they will recombine. No? They're going to recombine. So you're going to see electrons and holes recombining in this particular area. So when electrons and holes recombine, nawawala na yung free electron, nawawala na rin yung hole. No? So eventually, you have an area here. Okay, let me just redraw it here. No? You're going to have an area here that will be void of charge carriers. You're going to have an area that's going to be void of charge carriers. And you call this the depletion region. That is called the depletion region. No? So in the depletion region, okay, N is approximately equal to P is approximately equal to 0. You don't have any free electrons, okay, and you don't have any holes. Okay, on the other hand, the electrons, no, the electrons that recombine with the holes in this particular region is going to leave the right side. What? Is it going to be positively charged or is it going to be negatively charged? Kasi meron kang electrons dito, no? That recombined with the holes coming from here. The electrons here recombining with the holes here will cause this area to be positively charged, right? Okay, and because the electrons occupied holes here, no? So meron kang electrons dito, it occupied holes here, this area now is going to be net negatively charged. Okay, so to the right of the depletion region, dito sa kanan depletion region, okay, your region is positively charged. To the left of the depletion region, so remember your junction is in the middle, no? To the left of your depletion region, your area is negatively charged. No? Umalis dito yung electrons, kaya naging positive. Yung electrons pumunta rito, kaya naging negative. Okay. So I'm going to have a positively charged area and a negative charged area. So what do you expect to happen? I'm going to get now an electric field in this area. Okay. I'm going to get an electric field in that particular area. And the direction of my electric field is going to be from the right to the left. No? So, kakaroon na ako ng electric field here. No? Okay. What will happen when I have an electric field? So same question earlier. No? What will happen if I have an electric field? If I have an electric field, there's going to be drift. So this is going to cause drift. My electric field is going to cause drift. Now, what will happen? Electrons will drift opposite the direction of my electric field, no? And holes will drift along the direction of my electric field, right? Okay. So the drift will cause electrons going to the right. Okay, so if this is your electrons, it will go to the right. Okay, and if you have your holes will go to the left. So the drift is going to counteract the diffusion, and at equilibrium, I will be equal to 0. At equilibrium, the drift current and the diffusion current are going to cancel out each other. But at equilibrium, you now have a potential difference from your right side to your left side. Okay. You have higher potential of electrons from the right side to the left side. No? Okay. No. Sorry. Yeah, you're going to have a potential difference from your right side to the left side from the perspective of energy. Now, from the perspective of holes, or from the perspective of positive charges, you have a higher potential at the right than at the left, no? But from the perspective of negative charges, you have a higher potential at the left than at the right. So what's going to happen? No? What's going to happen is, okay, your energy bands are going to bend, no? Are going to bend so that the right side is going to be lower than the left side, because we're talking about energies of electrons. So this is what's going to happen. So this is originally this is what your band diagram looks like at the instant your junction was created. Okay, because of this exchange of because of the diffusion, okay, there's going to be a buildup of an electric field. Eventually, there's going to be a drift. Then after the drift, there's going to be a difference in potential between the right side and the left side, where the right side is going to be of a lower potential than the left side because we're talking about electrons. Okay, so this is what's going to happen. And in the end, if you take a look, these two Fermi levels are going to align with each other. The Fermi levels will align, which is consistent with what we said about the Fermi energy, no? The Fermi level. If you're talking about a solid, you can only have one value of a Fermi energy for that entire solid. So, pag tinignan nyo yung top diagram, ang nangyari niyan, okay, your right side and left side, basically, no, this side, you pulled it down. You pulled it down so that nagiging tapat yung Fermi levels nilang dalawa. And this is what it will look now at equilibrium. This is your energy band diagram of a p-n junction at equilibrium. And this area, essentially, this is your depletion region. That is your depletion region. Are there any questions? Any questions? I hope no nakuha ninyo why there is band bending. No. Okay. So I have a slide for that. So this is your depletion region. So in the depletion region, N is approximately equal to 0 and P is approximately equal to 0. There are no charge carriers here, right? Because the electrons from the N side recombined with the holes on the left side in that particular region, so that the net charge concentration is 0. And then that causes a potential difference now, because there's an electric field from the right to the left. And from the perspective of the electron, that electric field is going to lower the energy of the electron. Okay, and that lowering of the energy will cause the alignment of your Fermi level. Okay, and finally, this is how your energy band diagram will look at equilibrium. Okay, the difference in potential, okay. So there's a formula that has been derived for the difference in potential between E sub C on the right and E sub C on the left, no? And that will actually follow also, no? That's also the difference between E sub V on the right and E sub V on the left. Okay? And that formula is this, ano? First of all, this is an energy. So to convert voltage to energy, you have to multiply it by charge. Okay. Remember that voltage is energy per coulomb, ano? Joules per coulomb. Okay. So you multiply it by charge, you convert it to energy, and the formula for that energy is this, no? KT ln ND NA over NI squared, no? Where K, this is Boltzmann's constant. This is your temperature in degrees Kelvin. Okay, then you know ND, NA, and NI squared. ND is your donor concentration, NA is your acceptor concentration, NI is your intrinsic concentration. Okay, this is your electron charge, Q. Yung VBI, we call this our built-in potential. Okay, so this is for an open circuited PN junction. In other words, there's nothing connected to our PN junction. It's just existing by itself with nothing connected to it. Now, what will happen if we bias your PN junction? You bias your PN junction. So this is now my PN junction, where I emphasize the depletion region. By the way, no, the depletion region is usually a very, very small region. No? So this is usually very narrow. Okay, so here it is obviously exaggerated. Pero yung depletion region na yan, maliit lang na region yan. What will happen if I apply a voltage across my PN junction, where I apply a positive voltage at the P side with respect to the N side? No? Now, VA to VA should be less than VBI, so this is my built-in potential, for low-level injection. Actually, you never, if you have a PN junction, you never usually apply a voltage directly across it without a resistor. So the usual case is meron kang resistor dito, no? Pero so as not to complicate things at this point in time, we'll just assume that this VA, this value of VA, no, this value of VA is less than the built-in potential. What is VA going to do? No? If originally this was my equilibrium, okay, this is my equilibrium, where this is Q VBI. Okay. If VA is greater than 0, that is, if we apply a positive voltage at the P with respect to the N, okay, this is going to decrease. No? The value of this now is going to be Q VBI minus piece of A. In other words, okay, yung bending natin, okay, yung bending natin liliit. Okay? yung bending natin liliit. Okay. By the way, this is when we do this, okay, this is no longer in equilibrium because you already applied an electric field. No? So when you apply yung Fermi levels na ngayon natin, because this is not in equilibrium, you can have a difference between the left side and the right side. Itong W prime, no? Let me label the W prime, is going to be less than W. No? In other words, the depletion region becomes narrower. Okay. That is what will happen if I apply a voltage that is positive. If I apply a voltage that is negative, the opposite will happen. And dati, this is Q dBi. Ang mangyayari ngayon, this is going to be Q dBi plus dA. Because now I'm making the N side more positive with respect to the P side. Okay? Ito ngayon, okay, this now is going to get bigger. And my depletion region, I should label this W prime. No? W prime is going to be greater than W. No? The depletion region becomes wider. And it's easy to imagine this, ano? If this is negative, okay, if VA is negative, in other words, this is the positive, this is plus with respect to this, then I'm going to be attracting my electrons to the right, and I'm going to be attracting my holes to the left, no? Because this is going to be negative and this is going to be positive. And when I attract my electrons to the right and I attract my holes to the left, lalong lalaki itong depletion region na to. Lalo siyang lalaki. There's going to be less recombination because I'm pulling my electrons to the right here and pulling my holes to the left here. So that's what's happening here. Okay, from the perspective of current flow, this is what's going to happen. Okay, this is how things look at equilibrium. So these are my free electrons, okay, and these are my holes. So this is the position of the electron in the energy band diagram describes, okay, the energy possessed by that electron. And the position of the hole in the energy band diagram describes how much energy an electron needs to be able to occupy this hole. Okay, let's take a look here. No? Let's take a look here. This electron and this electron have the same energy. Okay, and that energy is greater than E sub C at all times. Meaning to say, this, okay, this is on the left, okay, this can drift. This can drift. And then ito naman, nasa kanan, okay, this can diffuse. On the other hand, if I take a look at these electrons here, this cannot diffuse. Bakit, no? Why can't this diffuse? If this try to go to the left to diffuse, at this point, it's going to see that to occupy the left side, it has to have greater than this amount of energy. So this forms an energy barrier. No? This is an energy barrier. So itong mga electrons na to, hindi makakapunta dito sa kaliwa. because of this energy barrier. Ito lang yung makakapunta sa kaliwa, no? Kasi mas malaki yung energy niya kaysa dito sa east of C. Okay, so in this particular situation, this can diffuse, this can drift, they will just cancel out each other. So your I due to N will be equal to 0. Okay, you have a similar situation for the holes. No? So this can drift, this can diffuse, but these holes cannot diffuse. Dahil pagdating naman dito, okay, ito naman yung energy barrier ng holes, no? The energy barrier of the hole is opposite the energy barrier of the electron. So this is the energy barrier of your hole. So these holes cannot diffuse. And that's why from the perspective of I sub P is also equal to 0. Kasi ito, maka-counteract lang nito, no? Now, what happens when you forward bias? So ito ngayon, this is your forward bias. So ito, this can drift. But now, all of this can diffuse. Right? Kasi pag tinignan mo yung energy nito, it will be enough to overcome this energy barrier, all of these three. Ito, hindi pa rin kaya, no? This cannot diffuse. But anyway, so there's net electron flow. There will be electron flow this way. Because more electrons can diffuse than the electrons from this side that can drift. So your net electron flow is going to be left to right. On the other hand, ganun din yung situation dito, no? You're going to have net hole flow. No? You're going to have net hole flow. And therefore, you're going to have a net current this way. There's a net current from the P side to the N side. And that current is because your diffusion current is going to be bigger than your drift current. Your net current is because your diffusion current is going to be bigger than your drift current. Okay, ano mangyayari ngayon pag naka-reverse bias? Okay. So that ito, makaka-diffuse pa rin, makaka-drift pa rin to. So this can drift. Okay, but now, all of this now cannot diffuse. None of this will be able to diffuse because of this energy barrier. Okay, so there's going to be electron flow in this direction, no? Net electron flow. Kasi pwede mag-drift yung electron from left to right, pero hindi pwede mag-drift yung electrons from right to left, so net electron flow. However, these electrons, this is an electron on the P side, no? So itong electron na to, these are what we call intrinsic electrons. They are the ones due to your intrinsic concentration, because remember that this is a p-type. No? So if there's an electron in the p-type, it's only due to your intrinsic concentration. Okay, and your intrinsic concentration is very small, and therefore your current, the current that will flow, okay, will be very, very small. No? So if your net current flow is this way, okay, your current is going to be this way, opposite the direction of, okay, because this is going to travel to the right, so your current is going to go to the left, and it is going to be very, very small. In fact, we call this your reverse saturation current. That is your current due to intrinsic electrons. And you have the same situation with holes. None of these holes now can diffuse. Okay, so where am I now? So current flow in a PN junction. So if it is forward biased, current will flow due to diffusion. No? And then if it is reverse biased, a very small current practically equal to 0 will flow due to drift. Okay, if you take a look at this current component, let's say if this is forward bias, no? Forward bias. Okay, if this is your junction, this is your P side, P type, this is your N type. Let's say this is your depletion region. In the N type, okay, if you take a look at, let's say this is N, no? If this is your concentration, N, this is going to be equal to N's of D. And then we said that there's going to be diffusion. Okay, what's going to happen to those electrons? As soon as the electron enters the depletion region, so I'm looking here at N, no? This is your plot of N, no? Your electron concentration. The value of that is going to be N's of D. As soon as that electron enters the depletion region, all of a sudden, okay, it's going to see, yeah, it's oh, no, sorry, forget that, no? But anyway, pagdating dito, okay, then there are electrons. This is not what we call electron injection. There's going to be electron injection dito sa P side. So this is now your P type. And then you're going to get now your exponential decay. Okay, so this is what N will look like here. And this is what will cause your diffusion. Diffusion of electrons. Okay, and then you have a similar situation with your holes. I'll use a different color so that it's not confusing. Okay, let's say this is your well, let's just say this is your whole concentration here. No? So this is P, and then this is now Na. So pagdating dito, this is going to be exponential also this way. It's going to be exponential that way. Okay, and this is what's going to cause the diffusion of holes. So your current in a forward bias junction is due to diffusion. Now, diffusion of electrons on the left, so this is your ice of n. Diffusion of holes on the right, so this is your ice of p, the same direction. Okay, so your current direction will be this way. No? This is your current direction. Okay, we're not going to go through the derivation, but you see exponential decays here, no? That sort of gives you a hint that your current components are going to be exponential in nature. No? So what is the current what is the relationship between voltage and current in a p-n junction? Okay. This is the relationship that was derived by Shockley, one of the pioneers of semiconductors. Okay, so this is the diode. This is called Shockley's diode equation. This relates the diode current to the bias. V sub D is your voltage across the junction. I sub D is the current through the junction. I sub S is your reverse saturation current. So the reverse saturation current, this is very, very small. This is the current that will flow if your diode were reverse biased, were substantially reverse biased. And this is current only due to intrinsic carriers. So the value of your reverse saturation current is anywhere from 10 to the minus 9 to 10 to the minus 15 amperes. And then you have an ideality factor, which is eta. This is a number between 1 and 2. This is to take into consideration during the fabrication process the imperfections in the semiconductor processes. For diodes that are well fabricated, we use eta is equal to 1. And then V sub T is your thermal voltage. V sub T is kT over Q. K is Boltzmann's constant. T is temperature. In degrees Kelvin, Q is charge. And we approximate VT to be 26 millivolts at 27 degrees centigrade. So this is where I want to end in the discussion of p-n junctions. Okay. So are there any questions? Maybe a lot. Maybe it's going to take you time to digest this. Any questions? Okay, so that's all I have prepared for this afternoon. So next session, I'm going to answer whatever questions you might have. If there are questions that come to mind as you go through this material again, please ask it next session. Otherwise, we'll have a short discussion on the bipolar junction transistor. Okay. Okay, so I will close the session as soon as the last person leaves. Thank you.
Thank you, sir.
Thank you,
Thank
sir.
you,
Thank you so
sir.
much, sir.
You're welcome. You're
Yes,
welcome.
sir.
Sir, I have a question now.
Sure, no problem.
For the formulas you gave us for current density and the one with built-in potential, you
Mhm.
said electron charge is equal to 1.6 times 10 raised to negative 19 coulombs. Will
Yes,
we be using negative 1.6 times 10?
I
Or
sorry. That's right. No, it's
Yeah.
negative. It's negative
Okay.
because electrons are negatively charged. I was just talking about the magnitude. Sorry.
All right. Okay. Thank you.
Thank you also.
Sir, yun sa diffusion, yun sa last part, sir, diffusion.
Ah,
Hindi, di ba sir, sabi, magdi-diffuse kapag forward bias, hindi po ba magdi-drift din? Kasi,
medyo confusing ano.
oh,
Magdi-diffuse siya, hindi magdi-drift, no? Pag forward biased. Gusto mong ulitin ko yung part na yon?
Sige, sir.
Sige, sige. Ito naintindihan mo, no? Naintindihan mo how this was gotten?
Apo, apo.
Dahil sa this is at open circuit, wala pang bias to.
Yes,
Okay.
sir.
Dahil sa initial diffusion, 'di ba, may holes from the right that diffuse to the left, may electrons from the left that may holes from the left that diffuse to the right, may electrons from the right that diffuse to the left. Magkakaroon ka ng potential between the right side and the left side, which will cause the bands to bend, ano? Okay? Okay, so ito ngayon yung value nung built-in potential. Okay, ito ngayon yung bias. So this is, if VA is positive, then you're making P positive with respect to N, ano? Okay? So ang mangyayari pag forward bias, ito, no? Lumiliit ito. Okay? Lumiliit ito at saka ito nagiging mas narrow, no? Itong W. Okay? So ang effect niyan is this, ito. Okay? Drift is when there's an electric field. Diffusion is when there is non-uniform concentration of charge. No? Okay. Itong nasa kaliwa, this will be due to drift. This will be due to drift, no? Because there's an electric field. There's an electric field due to the bias. That electric field is pulling is pushing away the electrons at the positive side, okay, and attracting the electrons toward the negative side. No? Pag tinignan mo yung bias, ito yung bias. Di meron kang electron dito, no? I'm showing an electron here sa P, right? Ito, this is an electron. I'm showing it in the P side. So itong plus is trying to sorry, teka. No, sorry.
Okay lang po.
No. Ito dapat ang tignan natin, no? Itong electric field na to. Okay? Because this is the electric field that is existing in the depletion region. No? Sa depletion region, ito yung electric field na nag-exist. Okay? Hindi dapat natin tignan tong volts na to, no? So dito sa depletion region, there's going to be an electric field that exists in this direction. Okay? So kung meron kang electron dito, itong electron will tend to flow, okay, opposite the direction of the electric field. No? If you take a look from the point of view of this hill, para siyang nahuhulog. You might think of this as a hill. Ito na lang, no? Mas maganda tignan dito kasi mas maganda tignan dito, no? If I had an electron here, this is the difference in energy. This is going to be my kinetic energy. Habang pumupunta siya sa kanan, tumataas yung kinetic energy niya. So itong electron na to parang nahuhulog. It's like it's falling down. That's why we say electrons tend to fall down, no? And that's drift. Drift yan, no? Pero ito, what will cause these electrons to flow? These electrons will flow actually, in fact, opposite the direction of the yeah, no, together with the direction of the electric field, which is really no, parang counterintuitive. What will really cause these electrons to flow is dito napakadami ng electrons. Dito konti lang. And therefore there's a tendency for these electrons to diffuse. And they
Okay.
can diffuse because they have enough energy, no? These electrons have enough energy so that kahit na nandito siya sa kanan, okay, it will be able to surmount this hill. Nakuha mo yung sinasabi ko?
Aba.
Medyo nakaka-confuse, no? But when the flow is because of a non-uniform concentration, it's diffusion. No? So kagaya dito, no? So yung electrons dito, okay, are now here. Okay, and then all of a sudden na-inject dito, and then magkakaroon ka ng non-uniform concentration dito. But because of this non-uniform concentration, you have a continuous drift. So yung current dito is proportional dito sa dndx. No? Just like the current here will be proportional to dpdx. It will be due to diffusion. Sorry, diffusion.
Yun, aba. Kala ko kasi nabanggit niya yung drift. So, kala
No,
nagdi-drift
diffusion.
yun, aba.
Diffusion. Sorry. Medyo
So,
nalilito na rin ako when I say diffusion and drift.
magkakaroon pa rin po ba ng drift dun sa forbidden energy gap? Ay, sa depletion region. Magkakaroon po ba rin ba ng drift?
Kasi ang value nung N at saka P dito is 0 eh. No. Mahirap, actually, that's one thing na mahirap i-imagine, ano? You don't have any charge carriers here. That's why pag nakikita mo yung mga libro, in this region, they're not going to show you a graph for N or a graph for P. No? Kasi for example, if you have an electron here, no, and it's going to diffuse here, parang all of a sudden, halos instantaneously, sandali lang siya dito sa depletion region. All of a sudden, it's going to appear to the left of the depletion region. So wala siya talagang time to stay in the depletion region. Yun ang nangyayari it's a little hard to imagine, ano? But that's what happens in the, kasi this is think about it, this is quantum level physics, no? Pero yun, ang nangyayari, okay, yung electron mo pagdating dito, all of a sudden it just appears on the other side, no? Parang hindi siya namamalagi dito sa depletion region.
Okay.
That's why
Ayun.
for all intents and purposes, you can consider this to be like dimensionless. Eh. So parang biglang nandun na siya sa kabila, no? That's how you can imagine it.
Yun, okay naman po. Nasagot ko yung tanong.
Kasi pag lalo na when you get to mga MOS transistors and all, that's a little hard to imagine, ano? How can current flow? Ang magandang tanong dyan is, how can current flow through this area when there are no charge carriers? But it can, no? The charge carriers, as soon as they enter that region, just appear right away, right outside the region. Anyway, ganun ang sagot, Ron. Mahirap i-imagine, no? Are there any more questions?
I have one last question po. Will there be lectures, like video lectures given to us this second week, or will it just be the modules?
I think baka may the handler might be preparing something. I'm not sure, no? Okay. I'm not sure. Okay. Anyway, sorry, I have to close the session because I have a class after this.
Thank you, sir.
Yeah, if you have additional questions, you can ask through Piazza or ano, no? Or maybe the start of the next class. Okay.
Thank you, sir.
Okay, you're welcome.